I'm going to record this lesson. So we're trying to find the angle x that produces a sine value of square root of 3 over 2. So the first thing we should do in this situation is decide what quadrant this is going to be in. So we want to go back to ASTC, all students take calculus, that little mnemonic device we use to decide what quadrant the trig functions fall into. So it's either going to be quadrant 1 or quadrant 2. So I can show you how to find both of those angles because there's going to be one in each quadrant. So let's review what the trig functions really mean, what they're really having us find. So in general, the sine of an angle, I want to just use theta in this case. It is y over r. So in the case of square root of 3 over 2, square root of 3 would be ry, and r would be 2. So r is always going to be the hypotenuse. If it were a unit circle, we would have different values, but this isn't strictly going to be the unit circle because we have a hypotenuse of 2 and not 1. So I want to just start with maybe the first quadrant. So I want to sketch this triangle. So our y value is going to be square root of 3. And r is going to be 2. So r would be maybe around here. And then I've just done these enough times that I recognize that the base of this should be 1, but we can verify that with the Pythagorean theorem. If we don't know what x is, we can just do x squared plus square root of 3 squared equals the hypotenuse squared. So x squared plus 3 equals 4. So then we subtract 3 from both sides. We get x squared equals 1. So then you might notice that we get x is plus 1 and minus 1. So that just corresponds to the fact that we have a triangle in quadrant 1 and a triangle in quadrant 2. So if we were to draw the same triangle in quadrant 2, the measures would be all the same except x would be a negative value. So if we are in quadrant 2, then x would be negative 1. If we are in quadrant 1, x would be positive 1. So now that we have the triangle drawn, we want to ask ourselves, well, what kind of a triangle is this? So this is one of those special right triangles. We know that it's not 45, 45, 90, so it has to be 30, 60, 90. So how do we know if this is a 30-degree angle or a 60-degree angle?
I'm not sure.
Well, the 30-degree angle is going to be the skinny one. So we notice how we have, in addition to the 90, we have a really small angle and then we have a larger angle. So the larger angle is going to be the 60. So up top is 30. So then this one has to be 60 degrees down here. So in this case, our angle has to be 60 degrees.
Oh yeah, okay, that makes sense. Wait, but then okay, yeah.
And if they want radians, that would be pi over 3.
Okay.
And just in case we wanted the other one, we could say this is equal to, well, if we counted multiples of pi over 3, this would be 1 pi over 3, and then 2 pi over 3 would be right here. So this angle right here would be 2 pi over 3. So these are the two angles that solve this. So going back to our original notation, using x instead of theta for the angle, x would be pi over 3, and x would be 2 pi over 3 as well. So these are the two solutions.
Okay.
Is it all right if I erase this?
Not yet. But then, is it okay if I use the unit circle?
Yeah, definitely.
Okay.
In that case, we'd have to modify the sides of our triangle a little bit. So for example, instead of a 2, we would make this into a 1. And then
Yeah.
square root of 3 over 2, and then this would be 1/2. But yeah, you could definitely use the unit circle if you'd like to.
Okay. Yeah, you can erase it now.
All right, so let's do a few examples. So well, actually, you know what? Before we do that, let's go to page 396 in the book and let's do the vocab check real quick. There's only 3 of those. So the first question says the equation 2 times sine of theta plus 1 equals 0. Here, I'm going to write this. Here, and I'll write the page number as well. We're doing the 5.3 exercises. This is the first vocabulary check. So 2 times sine of theta plus 1 equals 0. Has the solutions theta is 7 pi over 6 plus 2n pi, and theta equals 11 pi over 6 plus 2n pi, which are called what solutions? So this one would be real solutions. Trigonometry equations can have imaginary solutions just like other types of functions can. They can have extraneous solutions, and in this case, I don't think in this class we're really going to be getting into the imaginary values, but they definitely do exist. But for this particular problem, those would be real solutions.
Okay.
So on to the next one. The equation 2 times the tangent squared x. Here, I'll write this one. Minus 3 tangent x plus 1 equals 0 is a trigonometric equation that is of blank type. So this looks kind of familiar. It looks familiar to something we were doing before getting into the trigonometry section. What does this kind of remind you of?
A quadratic.
Exactly. So this is a trig equation of the quadratic type. So what do you think about question number 3? A solution to an equation that does not satisfy the original equation is called a blank solution.
Extraneous.
Yep, exactly. I'm not sure. I don't think I'm going to write that, but that's just an extraneous solution. An equation, a solution to an equation that does not satisfy the original equation. So yep, that is extraneous. So let's go down to some of these exercises below. They make really good problems for review. So I'm looking at number 1. They want us to verify that these are all solutions. So our first equation given to us is 2 cosine of x minus 1 equals 0. And they give us 2 things. They give us x is pi over 3, and they give us 5 pi over 3. 2 values. So you might want to just plug things in right away, but it might be a little bit easier to simplify it first. So I'm thinking I'd start by adding 1 to both sides and then dividing by 2. And then dividing 2 on both sides, we get cosine of x is 1/2. So now we just want to recall the place in the unit circle that has a cosine of 1/2. And in cases like this, it's useful to have the unit circle at your disposal because in the unit circle, the x is always going to be the cosine. So we need to recall for what angle is x going to be 1/2. So it would be this angle. So this would be 60 degrees, which is what they have as well. We just have I just put it in degree form, but it's the same as pi over 3. So our first one checks out. Now we want to check x2 as well and make sure that's a true solution to the equation. So where is 5 pi over 3 going to go on the unit circle?
In quadrant 3.
I'm thinking it will be quadrant 4. And the reason why is because this angle right here, I'm going to label it as theta. Theta is pi over 3. 2 pi over 3 is going to be right about here. And then 3 pi over 3 is going to be along the axis. So this is 3 pi over 3. And then we have 4 pi over 3. And then 5 pi over 3 is right here. And we know we're in the right place because 6 pi over 3 is 1 full revolution. 6 pi over 3 is going to be the same as 0. So it makes sense that 5 pi over 3 is just one multiple less than 2 pi. 1 multiple less than 1 full revolution. So it looks like we have, the exact same information. The only thing we want to make sure is that the parity is being preserved here. And what I mean by that is just parity is just whether something is odd or even. We want to make sure that where the function is, we want to make sure it's even where it's supposed to be and odd where it's supposed to be. So obviously if quadrant 2 would not work because cosine is negative in this quadrant. Same thing with quadrant 3. So definitely checks out. We expect cosine to be positive in both of these quadrants. So yeah, their answers definitely do check out. These are both correct. Is it all right if I erase this?
Mm-hmm.
How would you like to try the next one? Let's actually skip number 2. Let's go down to number 3. We have 3 times the tangent squared of 2x. Minus 1 equals 0. And the two values we're given are pi over 12 and 5 pi over 12. So how do we verify these values?
We should first simplify the equation.
Mm-hmm. Exactly. So what do we get when we simplify?
Tangent 2x is equal to 1 over root 3.
Mm-hmm. So now that we have it in this form, let's compare this with not tangent of 2x, but with tangent of x equals 1 over root 3. So they'd be similar, but the 2x on the inside means that our period is shrunk by a factor of 2. The 2x means that we can fit 2 periods into the space that we would normally fit just 1. So ordinarily, we should have pi over 6 in 5 pi over 6 if this is our equation. Tangent of pi over 6 is 1 over square root of 3. And tangent of 5 pi over 6 is also 1 over square root of 3. So it makes sense that we cut the period in half. that our new values would be not pi over 6, pi over 12. And not 5 pi over 6, but 5 pi over 12. So that's how we confirm the validity of these two. We just have to ask ourselves, well, what's going on with the period? What kind of changes are being made to the period when we go from x, tangent of x to tangent of 2x? So that's how we do things with the change in period. So this one, we're able to validify both of those, or validate, I guess is the right word. Validate.
So they're the same?
Well, they're not exactly the same. Well, the values are the same. Yeah, we get 1 over square root of 3. But if it were just tangent of x, you would get pi over 6 and 5 pi over 6. So it makes sense that if we were to have a 2x instead of an x, that our period would be cut in half, and therefore we would have pi over 2 times 6 and 5 pi over 2 times 6. So that's why these values have a 12 as the denominator instead of a 6, because we have a different period. It's just the period, the change in period that makes this pi over 12 instead of pi over 6.
Okay.
Let's try another one. How about 2 sine squared of x minus sine squared of x minus 1? So for this one, it might be just a little bit easier to solve it ourselves and see if we get the same two answers that they're providing us. So we have a 2 sine squared of x minus sine of x minus 1 equals 0. How do we solve something like this?
First, we can move the 1 to the other side.
Well, actually, I'm thinking this problem is of a really special type. Do you see something kind of familiar about it?
Oh, the quadratic.
Yep, we want to approach it like we would a quadratic. So I think the first thing we might want to do is to rewrite sine of x so that it's just x. We might just want to factor this expression, and then once we have it factored, we will replace x with sine of x. So see if you can factor this expression.
Okay. I got 2x plus 1 times x minus 1 equals 0. And then we have to replace that with the sign, extra sign.
So we want to set each of these factors equal to 0. So we want to set 2 times sine of x plus 1 equal to 0, and that will give us our first solution. So let's start by subtracting 1 from both sides and then dividing by 2. So then we get sine of x is negative 1/2. And going to the unit circle, there are 2 angles that have these values. One of them is in quadrant 3 and the other one is in quadrant 4. They would be these two. So this has to be 7 pi over 6. And then the other one has to be, well, this is 1 pi over 6 less than 1 full revolution. So this has to be 11 pi over 6. So let's see if that's the same answer they have. Oh, they have pi over 2. And that doesn't make a whole lot of sense because pi over 2 is this right here. X is 0, y is 1. So it looks like only one of their solutions is correct. Or actually, hang on a second. I forgot that other one. We actually have another solution too. So I want to erase the one we've already found. And I forgot about our other factor. Our other factor is sine of x minus 1 equals 0. So I want to add 1 to both sides, so we get sine of x equals 1. So then pi over 2 would definitely work. Because if our angle is pi over 2, our x is 0, our y is 1, and in the unit circle, the y is always going to be the sine value, the x is always going to be the cosine value. So this is definitely true just by plotting it on the unit circle. If we were to plug in 1, we would get this. If we were to plug in pi over 2, we would get 1. So yeah, it looks like they have the right answers. All right. Hang on, I think I lost the page. My iPad does that sometimes. Sometimes it just changes the page for no reason. So let me go back real quick. All right. Let's have you try what would be a good one. Maybe 2 cosine of x plus 1 equals 0. So for this one, I'd be okay with just one solution. If we're talking about the full unit circle, we should have 2. One in one quadrant and then another in a different quadrant. But for now, let's just have one solution. So how would you solve this?
I would isolate the cosine of x.
All right. All right, looks good. So let's recall what the ratio for cosine is. Cosine would be x over r. So if we're in the unit circle, r is 1. We could think of it as just being x in that case. So we want to find the place in the unit circle where x is equal to 1. No, actually, it would be equal to 1/2. Negative 1/2. So we know x should be negative 1/2. So It's going to be down to quadrant 2 and quadrant 3. So if x is 1/2, or sorry, if x is negative 1/2, what is y going to be?
Root 3.
Yep. Oh, not just root 3, but root 3 over 2. In the unit circle, the x and the y are both going to have denominators of 2. And then, of course, the unit circle, our radius is 1. So this would be one value. Another one would just be the reflected value. So we would have either 2 pi over 3, or we would have 4 pi over 3. So those would be the two solutions to this one. We'll just use that as our solution. I think we should try number 9. We have square root of 3 times the cosecant of x minus 2 equals 0. So what do we want to do first in this one?
Isolate the cosecant.
Mm-hmm. Exactly. So let's see what that looks like.
I actually had this on for my homework.
Oh yeah? Did you get it?
Yeah,
What was your answer?
I got pi over 3 and 2 pi over 3.
All right. So I want to see if I get the same thing. So we have cosine of x is 2 over root 3. Or cosecant is what I meant to say. Cosecant of x, 2 over root 3, which means sine of x would be square root of 3 over 2. So the unit circle would have this triangle be in the first 2 quadrants. So if it were 1/2, that would be pi over 6. So yeah, I got the same thing you have, pi over 3 and 2 pi over 3. Very good. Nicely done. How about this one? How about cosine cubed x equals cosine of x? We want to find all solutions. So how do we do it?
I don't know.
So we can start by eliminating a cosine of x because we have cosine of x to the third and then we have cosine of x to the first. So we can divide cosine of x on both sides, so we get cosine square root of x equals 1. And then we can take the square root of both sides. cosine of x equals 1. There's only one angle for which this is true, and that would be 0. So the solution to this one is 0. Or 2 pi. How about 3 times tangent cubed x equals tangent of x? How do we solve something like this?
We could divide by 3 on each side.
All right, but before we do that, we might want to start by dividing both sides by tangent of x. Then we're going to have 3 tangent squared x equals 1. And then we can divide by 3, so we would get tangent squared x is 1/3. And then we can take the square root of both sides, so we get tangent of x is 1 over square root of 3. And if you recall the quotient identity, tangent of x is just sine of x over cosine of x. So we want to find the place in the unit circle where the sine is equal to 1 and where the cosine is equal to pi over 3. How would we find that?
We're able to draw it.
So we know tangent is positive, which means it's either going to be in quadrant 1 or in quadrant 3. So that means our x should be positive square root of 3. Our sine should be positive 1. Or either they're both positive or they're both negative. So a y being 1 would be right around here. Nope. It would look like this. And then the other place where this is true would be right here. So for just an ordinary triangle, the hypotenuse would be 2 in both cases, but if we adapt this to fit the unit circle, we would have 1, 1, and then we would have square root of 3 over 2, 1/2, and then negative square root of 3 over 2, and negative 1/2. So both of these angles are solutions. We have pi over 6, and then this other one would be 7 pi over 6.
Oh, wait, can I finish writing that down?
Oh, sorry.
Okay.
Let's have you try number 30. We have 2 times sine squared x plus 3 sine of x plus 1 plus 1 equals 0. What are you thinking might be helpful in this situation?
Putting it into a quadratic first.
Yep, exactly. So we have a leading coefficient that's not 1. So it looks like we're going to need to split the middle term. I'm thinking we might want to split it up into a 2 sine of x and a sine of x, because then we'll be able to factor by grouping and get an equivalent expression in both factors. So where did you get that sine of 1 from?
Sine of x.
Oh. So what do we get when we solve that first factor for x?
For the first one, it would be -1/2.
All right. Sine of x is -1/2. So whenever we have 1/2, whenever the sine is 1/2, it means we're going to have a skinny triangle. We're going to have a triangle that's close to the y-axis, which means that we're going to have either this one, or this one, or that one. So it really depends on the sign of this, the SIGN, whether it's positive or negative. But whenever sine is 1/2 or -1/2, it has to be one of these 30-degree angles. So we know that it has to be -1/2, so we can instantly rule out these two. So the two values that it could be would be, well, this is, you can either call it 150 degrees, or this is 5 pi over 6. And then what about the one beneath it? What would be the radian form of this negative part? Or actually, hang on a second. It's not going to be the one on top. It's going to be one of the two on the bottom. Sine is negative. Made a mistake there. So it's actually going to be one of these two. So how do we figure out what angle this is?
It's going to be a 30-degree.
So if half of a rotation is pi, and this is, we're adding another pi over 6 to that. So this would be 6 pi over 6 plus 1 more pi over 6. So 7 pi over 6, right? And then this one, if one full revolution is 12 pi over 6, this is one less than that. So this would be 12 pi over 6 minus pi over 6, so that would be 11 pi over 6.
Can you explain that one more time?
Sure. So I agree with the way you've set this up. We have sine of x is -1/2. So we first want to identify the quadrants these are going to be part of. So sine is negative, it's going to be one of the bottom two quadrants. So it has to be quadrant 3 or quadrant 4. So from here we want to, well, we have sine of x is going to be 1/2, and whenever sine is 1/2, it means we're going to make a skinny triangle. We're going to make a triangle that is really close to the x-axis. So whenever sine is 1/2, we're going to have some multiple of pi over 6, or in degree form, it would be some multiple of 30. And we can verify that just by plugging in the values. We know this is going to be a 30, 60, 90 triangle, where we know the x is going to be negative and the y is also going to be negative. So we have, this would be -1/2. This would be negative square root of 3 over 2. And then this is a unit circle, so the hypotenuse would be 1. And we know this is correct because this, if we're in the unit circle, the sine is always equal to the y component. So we verified that this is correct. So the question is just, what angle is this? So we know that halfway around the unit circle is pi, right? So we can call that 6 pi over 6. Halfway through the unit circle is just 6 pi over 6. So we're going to use that to help us. So we want to add 1 more pi over 6 to 6 pi over 6. So what do we get when we do that? What is 6 pi over 6 plus pi over 6?
7 pi over 6.
Yep, exactly. So halfway around the circle is 6 pi over 6, but if we were to add this part as well, we would be going to 7 pi over 6. So that's our angle for this case. And then there's another place where it's true as well. It would be right here. So the only difference between these two triangles is that in this one, the x would be positive. The y is still going to be -1/2, but the x this time is going to be positive square root of 3 over 2. Hypotenuse is still going to be 1. So the question is, what angle is this? So we can approach it the same way we did the last one. We know that 1 full revolution would be 12 pi over 6. So if 1 full revolution is 12 pi over 6, what's it going to be if we go not quite 1 full revolution? What if we stop right here? What would that angle be?
11.
Yep, 11 pi over 6. So these two angles pertain to our first factor. Now we want to do the same thing for our second one. So we want to solve it the same way we did the first two. So I want to erase some of the stuff we don't really need anymore. So we want to create an expression. Oops, meant to erase that as well. So we have sine of x plus 1 is 0. So if we subtract 1 from both sides, we get sine of x equals negative 1. And in the unit circle, the sine is always going to be the y-coordinate of the angle. So where on the unit circle is y going to be negative 1?
The bottom.
Mm-hmm. There's only one place where it reaches negative 1. It would be one of these quadrantal angles. This is 3 pi over 2. So whenever we reach a maximum or a minimum, we're only going to have one solution. If we were to reach a maximum, pi over 2 would be our only solution. We're reaching a minimum, so 3 pi over 2 is our only solution. So that's why our last thing we were solving had 2 solutions, but this only has 1. So our solutions would be 7 pi over 6, 11 pi over 6, and 3 pi over 2.
Okay.
These are the 2 solutions. So, how do you feel about this material? Do you feel fairly confident solving trig equations?
Yeah.
Yeah, I feel like you have a pretty good understanding of this. So I think we might spend our last 12 minutes or so reviewing the next topic. So we're going to skip down a few pages, and I'll let you know when I have the page number. So we're going to skip down to page 430. We're going to be talking about the law of sines, which is pretty useful in solving certain types of equations.
Okay.
My tablet's acting weird again.
Wait, I have a question.
Sure.
Until this week, will we get to like chapter 10?
Chapter 10. Oh, what chapter is that?
That's about like conics and lines and eclipse and
That's typically not covered in a pre-calc book. I mean, I was kind of surprised that it's in the this pre-calc textbook. I've never seen it be covered in a pre-calc class. It's typically just an Algebra 2 topic.
Okay.
So we're going to cover law of sines and law of cosines, and then there are a few more topics after that, including partial fractions decomposition. Oh, and vectors. We're going to cover vectors a little bit too. So we are talking about the law of sines, and it's useful for when we have certain information about a triangle and we're trying to find other information. And I think it's best illustrated with an example. So I want to start by writing the formula. We have A over the sine of A, sine of capital A, lowercase b over the sine of capital B. So lowercase b is a side length, capital B is an angle, and the same thing goes for A and C as well. So let's go to the next page. Let's do example number 1. We're given the following information. they tell us that C is a 102.3 degree angle. And that B is a 28.7 degree angle. And side length B is 27.4 feet. Find the remaining angles and sides. So we can start by finding angle A. We know that all of the angles in a triangle have to add up to 180. So let's just do 180 minus 102.3. And then minus 28.7. And we get 49. So angle A is 49 degrees. Now let's find side length C. So we want to use this part of the law of sines. So we want to substitute the values. We get something like this. And then we don't have side length C, but we do have angle C. So from here, we just want to multiply both sides by the sine of 102.3, and then evaluate, and then we have our angle. No, then we have our side length. So if we were to plug this into a calculator, we would get 55.75. And then if this were a right triangle, we could use the Pythagorean Theorem to find A. But the law of sines, it can be used in triangles that are not right triangles. We can actually use these in a situation involving any triangle. It doesn't have to be a right triangle. So now that we have all of our information except side length A, we want to use angle B and side length B to help us find side length A. So our side length A would just be sine of angle A divided by sine of angle B times side length B. So we have sine of 49 over sine of 28.7 times 27.4. And for that, we would get 43.06 feet. So we're going to cover the law of cosines now. And the law of cosines is a bit more complicated than the law of sines. Do you have any questions on this before we move on?
No.
All right. Law of cosines looks like this. So it's a lot more complicated than the law of sines. There is a lot more work involved. So if there is an opportunity to solve a problem only using the law of sines, then we definitely want to do that. And we don't really have enough time to do any examples of this, so this is what we're going to do in the next lesson. We're going to just start with this. Some examples of the law of cosines. So no homework for tonight. If you don't have any questions, you're free to go whenever you have this copied out.
So since I didn't take algebra 2 yet, and you said you can make a video of what I wanted to learn. So if we don't get through everything in this textbook, can you do that?
Yeah. What did you have in mind?
Like I said, the last chapter.
Oh, conics.
Yeah.
Sure. No problem.
Okay, thank you.
Yep, you're welcome. See you next time.
See you tomorrow.